Kumar and Geoffrey. And Geoffrey is the
Hello, thank you for coming. I'll be talking about a construction for these objects called relaxed locally correctable codes. And if you've heard of local testing, where it's going to be really important, this is a joint work with Vinayak, who's sitting in front. Right, so the story of this kind of starts with locally decodable codes or locally correctable codes. They're sort of these two like very closely related notions. And they're basically error correcting codes that have correctors that let you correct by only looking at a very tiny part of the input. So sort of what's going on is that if you have some kind of, or you have an input string W, which has some bounded corruption from the locally correctable code, here's a capital C, then for any index I, which you want to correct from W, you give the index to this algorithm, and the algorithm decides on some Q spots to look at in your input W. These are the only spots that it's going to be allowed to look at. And after it makes these queries, it should be able to spit out the corrected ith index of the closest code word with like a high probability, or it's like probability 2/3. And so this is, I mean, it should be pretty clear why this is a very desirable property. But the problem is that this is a very difficult problem. The optimal parameters for locally correctable codes are a very big mystery. In this talk, we'll be focusing on the asymptotically good setting, which is locally correctable codes that have constant rate and constant correcting radius. Correcting radius here is the delta, which is like how much corruption the corrector is able to handle. And so in this setting, when the rate and the correcting radius have to be constant, how many queries are needed by like the best possible LCC? And so in this setting, the lower bound that we have from the seminal work of Katz and Trevisan is like about roughly log. But the problem is that the upper bound is just slightly subpolynomial. It's like 2 to the root log n due to a swastik or a noga and Shivangi. And so there's like a very, you should be able to see there's like a big ocean between these two bounds. And it's like a very major open problem to close this gap. And just to emphasize how like difficult this problem is, if you look at sort of the history of asymptotically good LCCs, sort of like the first asymptotically good LCCs are like if you instantiate Reed-Muller with the right parameters, and you're able to get like some arbitrarily small polynomial number of queries. And then in the years following, there's like these 3 different ways to get asymptotically good LCCs with rate arbitrarily close to 1, but that still require like some polynomial number of queries. And finally, with the work of Swastik or Noga and Shivangi, we're able to have asymptotically good LCCs with the query complexity, which is slightly subpolynomial. But right, there's still this huge gap between the lower bound, which is log, and the upper bound, which is like 2 to the root log n. Right, so we have this huge gap. It's a really difficult problem. It's been open for like multiple decades. Like, what do we do? What can we do to like make any progress? Well, one way is to relax the definition and see if we can find anything cool. And so the way that we're going to relax this definition is that we're going to allow the local corrector, it doesn't have to return the correct answer anymore. We're going to allow it to give up if it detects some errors in the input. And so so like this might seem like if you haven't seen this before, it might seem like a sort of odd way of relaxing the definition, but I want to motivate it with sort of using proof systems as like the intuition. Like if you consider when you're trying to construct a PCP, it might be like a desirable property if the proofs from your code have good local properties. And what I mean by this is that like if you're given some instance X and you're given a proof pi, which is like a purported proof that supposedly X is in this language. Like one first thing you can do is if the proof is obvious garbage, then you can hope to like detect this with few queries and throw it away. And this is this notion of local testability, which has already come up a couple times today. And once you know that the proof is not obviously wrong, the next thing you can do is that you have to check that the proof actually corresponds to the instance. Like for example, if the proof is like a valid proof, but it's for an instance that has nothing to do with X, then you have to detect this case. And so this is intuitively where you could use something like local correctability to sort of extract some information to make sure that pi has something to do with X.
Twice the simplification.
Yes, yes. Yeah, local decodability. Here we use local correctability everywhere, but local decodability is is essentially the heart of what you need here.
So this is, I would assume, change the lower bound. It's not clear to me. Your goal is to change the upper bound, yeah?
Yes.
But wouldn't this be something people would have thought of? But you're saying that it would reject, it wouldn't satisfy them. Okay. Sorry, never mind. I answered my own question.
I think it'll. I'll in a couple more slides. I think it'll help. Right. So in this is sort of like the intuition for why local testability and local correctability are like useful properties. But if you notice that in this setting, if in the local correctability step you notice that there's some kind of error, you don't have to decode successfully anymore. You can say, okay, this proof like has an error in it. I don't even have to look at it anymore. I can just give up. And so this is sort of the motivation for this idea of relaxed locally correctable codes.
Okay. So what does the lower bound say about this?
The lower bound will be, so for LCC, lower bound is like log.
Definition. And does the lower bound still hold?
It'll be in a couple of our slides, yeah. Right, so formally, what is this definition of relaxed locally correctable codes? So this definition like first appeared in the relaxed locally decodable code form with Ben Sasson, Goldreich, Harsha, Suda, and Varan. And the formal definition is that you have this code, it's an error correcting code, and it has a corrector that makes Q queries such that when you give it an input, which has some bounded amount of corruption away from the code, then you have to either correct or you return this failure symbol bot. Right, but as is on the screen, this is a trivial definition because you can just return bot all the time. So to make it non-trivial, we require that the corrector should never reject a code word which is actually in the code. Right, so the work like Ben Sasson, Goldreich, Harsha, Suda, Vadan, when they introduced this definition, they showed that in the constant query regime, you already get a dramatic improvement over like the known LDCs with constant queries. So like we know that the relaxing this definition makes the problem more like we have better state of the art when we relax this definition in this way. But how can I like convince you that this definition actually is useful for anything? And it turns out that along the vein, like in the same vein as the sort of PCP sort of intuition, there actually are like quite a few applications where the RLCC definition suffices in place of the LCC definition. So sort of like in the just like proof system with locality setting, you can use RLCCs with like interactive oracle proofs or like proofs of proximity, like cases where you want locality. And some other places that you can use it are like in property testing, or when you have like data structures that where you want to be able to like detect when there's corruption in data structures.
I think I don't understand the definition. Are you allowed to give up at any point of time, like for the soundness part? MW of I is in.
Yes, you can. You either have to correct the specific bit, or you just return the failure symbol.
But I'm not allowed to do it all the time.
Yeah, this is a good question. The completeness means that if I give you like an input which has no corruption in it, you're never allowed to reject. Because otherwise you could just reject all the time. But the completeness makes it like actually a useful definition.
Thanks.
Or is this any more questions on the definition?
I guess one more question. So this is not simultaneous, right? So for every I, it has to be either correct or bottom. It's not that you're requiring that all of them will be bottom.
It's very important that you can be in either. Yeah, that's very important. Right. So my point is that this definition is actually useful, and there are places where you could use RLCCs in place of LCCs. So I told you that in the constant query regime, sort of the work that the BGHSVIA introduced this, showed this massive improvement in the constant query regime. So like how does this affect the asymptotically good regime that we study in this work?
about the LDC versus with the relaxed, or the read and the relaxed. Here there is no, if you have a small number of queries for the standard notion, the strict notion, it implies a notion of smoothness, right? That each query should be almost uniform. And here this doesn't imply
It's
such.
no longer smooth. Yeah, if you know a little bit about how the lower bounds for LDCs work, the RLDC is no longer smooth.
In fact, the upper bounds we construct are not smooth.
Yeah, they have to be not smooth.
There's a proof part and there's a code word part.
Right, so in the constant query regime, I didn't put it on the board, but I told you that there's a big improvement. In the asymptotically good regime, we also have a big improvement. So first, I'll start with like the lower bound. The work of like Gur and Lachish, they give the first lower bounds for these RLDCs or RLCCs. And the lower bound in the asymptotically good regime turns out to be that the queries have to be at least like square root of log. And so this lower bound is not that far from the known lower bound for like the full-fledged LCC. So the lower bound hasn't moved that much, but in the upper bound, we get a dramatic improvement. So if you take like the existing best LCCs that I mentioned before, you get like this subpoly, but with RLCCs, you can get all the way down to like quasi-polylogarithmic. So the gap, so this is the state of the art prior to our work, and the gap between the lower and upper bounds is already dramatically smaller than the gap in the full-fledged LCC setting. Right. So if you take a look at this, the lower bound is like polylogarithmic. The upper bound is really, really close to polylogarithmic. So maybe the truth is that it's polylogarithmic, and that's what we're able to show in this work, is that we get like a big exponent, but that the lower bound and upper bound are separated like polynomially close to each other. And after our work, Gil Cohn and Tal Yankovitz were able to further reduce the exponent to 2. So now the gap is very, very small, especially compared to the full-fledged LCC setting. Questions at this point? Okay. Right. So how does the construction work? The first thing I want to say is that the general approach we follow is the approach followed by the prior works as well. And so sort of a natural idea is that if we want an RLCC that has arbitrarily large block length, we can try to use some kind of induction. Like we can start with a trivially small RLCC, like an RLCC that has block length which is like constant or like polylog in the final block length. And this has like a local corrector because you can just read everything. And now that we have a tiny RLCC, we can try and build larger and larger block length RLCCs, sort of iteratively, as long as we have some operation which can take a code with small block length and lift it to an RLCC with slightly larger block length, we can repeat this until we get to the block length that we want. Right. And so this sort of like inductive idea was used by like both of the prior RLCC constructions for the asymptotically good regime, and we're going to also follow this approach. And okay, so now I want to say like a little bit about how the previous works work and how ours is able to get past like the barriers that they have. Right. So I'm going to focus on the like Gur, Ramnarayan, Rothblum construction, which is to use the iterated tensor product. If you've never seen the tensor product before, basically, if C is a linear code, then the code C tensor C is the linear code where every row is a code word of C and every column is a code word of C. This is like a sort of like a fundamental operation for building larger codes from smaller codes in coding theory. And so you would hope that because C tensor C has so much like structure from C, that some properties of C will also carry over to larger code. And it's exactly what they show, which is that when C is an RLCC, then C tensor C is also an RLCC. Right. So I'm going to go over at a very like high level. How does this work? The query complexity will grow by a multiplicative factor. I'll show you why. Right. So to show this, we have to give a local corrector for C tensor C that uses the fact that C has a local corrector. So like, what's a natural thing that we can try is that when we have this input, which we know is like has bounded corruption away from C tensor C, and I is sort of this index that we want to correct, then I is contained in the row. So let's just recurse on the smaller code's local corrector on the row that contains I. And so this will work as long as there's not too much corruption in this row. But the problem is that this row is such a tiny fraction of the entire input that this row could be complete garbage. It has nothing to do with the rest of the input. And so to combat this, we can pick some random columns, and we can recurse on the smaller code's local corrector and double check that the column agrees with the row. So this explains why, because they have to recurse on the smaller corrector polylog number of times, you're going to get an extra polylog factor every time you apply the tensor product. And because the tensor product squares the block length of the code, you have log n many iterations for this. That explains the log to the double log total query complexity. And the work of Cohn and Yankovitz is that they're able to, I can't get into like the technical details of how it works, but they're able to improve the query factor per step from polylog to polylog-log, which is where you get the log to the triple log. But the reason that I'm showing this on the slide is that I want to emphasize that these two techniques, they incur this multiplicative query overhead because you have to recurse on the smaller code's corrector multiple times. Because like tensoring and also the technique of Cohn and Yankovitz, which they call row evasive partitioning, they work because you're leveraging like this column against all of these rows. You want to test these overlapping parts of the input against each other. And at each step, we have to recurse multiple times. Specifically, we have to recurse like polylog many times or polylog-log many times. And because it's multiplicative, it accumulates, and it gets like that's why they're not able to reach like a polylog. And so, is there any hope that there's some kind of alternative to tensoring, which can grow the block length of an RLCC while preserving the relaxed local correctability, which only incurs an additive query cost? And another way to look at this is that they show that C tensor C, or that the row evasive partitioning gives a larger RLCC by leveraging like the relaxed local correctability of these smaller parts of the code against each other. So if you imagine, like, if you start off, you're like doubling down on the RLCCs that you already have, so they sort of become like more suboptimal over time. So what if you're able to, instead of like leveraging these smaller RLCCs against each other, what if you could like enlist some sort of outside help? And that's what we're able to do. We use this like very large hammer, which is locally testable codes. Locally testable codes has already come up a couple more times today, but just in case you haven't seen it, locally testable codes allow you to detect the corruption in the input with very few queries to the input. And like more formally, we have this local testing algorithm T, which makes like a few number of queries, Q queries, and the probability that you reject is proportional to how much corruption is present, or what the distance is from the code. And right, as similar to the RLCC definition, to make it non-trivial, you can't reject when you get an actual true code word. Right, so because of the recent work of like Denir, Evra, Livne, Lubotsky, Moses, we have these really great high-rate LTCs. We have this like big hammer, and let's try to use them to make better RLCCs. Are there any questions about the definition?
Can you go back? Sorry, the sketch I'm missing some part. So you're saying you look at this row, if this row has too many corruptions, then what you're just going to pick something like log n many positions in it and check if this is the case or something.
So sort of if the corruption in the row is really small, then you're fine. If the corruption in the row is really big, like an example is if you were to take a different code word, cut one row out, and then paste it on top of this code word. So if I only look at this row, you fooled me into thinking that I'm actually in the other code word. So the way to combat that is to pick some random columns, like polylog many columns, and then because if this row was like completely corrupted, now these random columns should be able to detect that.
Anybody see something that doesn't check out? Then
as soon as you see any like sniff of corruption, you can just give up immediately and you win.
Okay, that's using this redux.
Yes. Yes. And you can also sort of, I guess you can see here that the RLCC is not smooth because you're sort of drilling down on the area around the index that you want. Okay, so we have this really strong object, and maybe we can use these to make RLCCs. The way that we're going to use them, we have our operation for boosting the block length of an RLCC is we call it nesting. So the formal definition is if you have a code of smaller block length, like little n, so you have a smaller code C1, and you have a code of larger block length C2, and you should think of little n and big N as sort of like big N is like mildly larger than little n. So think of n as like half of big N or something like very, very mildly larger. We're also going to assume that little n divides big N. Then the definition is that the code formed by nesting C1 and C2, we use this like nested intersection notation is that you take the intersection of C2 and you take with the direct product of C1 sufficiently many times so that it type checks. Basically, C2 has block length big N, and C1 raised to this power also has block length big N, so everything is well defined. Before let me just put the picture up. I think it'll make it a bit more illustrative. Is that if you have a code C1, C2, small block length, big block length, then this code is made up of strings, which are code words of C2, but also where the first half is a code word of C1, and the second half is also a code word of C1. This is like the heart of our construction. I also want to mention that little n does not have to divide big N, but there's a bunch of padding technicalities which are not really in the scope of this presentation. Right, so why is this useful? The key lemma is that if you were to nest the smaller RLCC into a larger LTC, then you get a larger RLCC. And once you have this, you can sort of iterate and to get arbitrarily large block length. The formal statement is that if you have an RLCC and an LTC and they have essentially the same distance, if an RLCC has correcting radius delta, then it has distance delta. So you can think of the radius and distance of an RLCC as basically interchangeable. If an RLCC and an LTC have essentially the same distance, then by nesting the RLCC into the LTC, you can get a RLCC with the same block length as the LTC. And just repeat the picture from before. The code formed by nesting the RLCC in the LTC, it's going to be made up of the set of code words which are in the locally testable code, but where we have sort of these blocks, these intervals, which are, when you restrict those intervals, it's also a code word of the smaller RLCC.
No, I was just asking, these intervals, are they necessarily contiguous or just locations?
They don't have to be continuous, but it's simpler if you present them as continuous. Basically, you want to you want to cover 1 through n with these little n size intervals, and that's
the dimension. What happens with the dimension of the big one? The rate.
I'll show you the rate in a bit.
Is relax necessary for it? Suppose it was an LCC, then will the resultant be an LCC? LTs?
I don't think so. Just from the fact of losing smoothness, I think. Yeah, the rate calculation is important, and I'll show you in a couple more slides. Right, because if we want asymptotically good, we need the rate to be constant. So if this destroys the rate, then it's worthless. But I'll show you that it's okay. Right. So what does this like hybrid structure give us? Like, how do we show that this like LTC nest RLCC has a relaxed local corrector? To use the hybrid structure, we can use a local corrector that handles two cases. So basically, if the number of corrupted bits is really small, we only have to look at like a substring of the input. And if the number of corrupted bits is really large, then, well, we have this like really strong local tester, and we can catch that case. That's basically what's going to happen. Right. So starting with the first case, if the number of corrupted bits is less than like delta little n, right, we have this input w, which, okay, right. So if the number of corrupted bits is really small, then just by picking the appropriate substring, which contains the index that we want, we already know that the distance in this substring is low enough that we can recurse on the smaller local corrector. So because, like, in the worst case, all of the corrupted bits will be in this interval, but then you normalize by little n, and the distance is now delta, which is the correcting radius of the smaller RLCC. And also, the closest code word when restricted to this interval is also a code word of the smaller RLCC. So we can just recurse on this substring, and we're done. Right, so great. We have this close case. When the number of corrupted bits is really small, we can just focus on the interval. But in the other case, when the corrupted bits is large, then the distance from the code is also large, and we know that the local tester will reject with probability proportional to the distance from the code. So we just have to run the local tester the appropriate number of times to find the corruption with a constant probability. Right, so that's great. If we know we're in the close case, we can just like drill down into this substring. If we know in the far case, we can use the local tester and it will catch the corruption. But a priori, we don't know which case we're in, but we can just put them together. We can run the local tester the sufficient number of times, and we can recurse. And if in the first step the local tester finds corruption, we win. If the local tester doesn't find corruption, then we're probably in the case with low corruption, and then we can RLCC corrector guarantee is satisfied, and we win in that case as well. So here you can see that this nesting operation only incurs an additive cost in queries. We have sort of this tail recursion because we're only recursing on the smaller code once. And we're sort of adding this extra testing step, but because we only recurse on it once, it becomes like an additive cost in queries. This is why we're able to get additive cost, which ultimately leads to polylogarithmic queries. So just in summary, we have this big LTC and a small RLCC. And by nesting them together, we're able to get an RLCC which with the larger block length, with essentially with the preserved correcting radius, it doesn't deteriorate, and with queries that only goes up by an additive factor. So here, there's like one parameter which is really important that I haven't mentioned yet, which is what happens to the rate when you apply this nesting operation. So the rate will also go down by an additive factor if LTC and RLCC are linear, because just by like rank nullity theorem, you count how many linear constraints in like the naive way, and they just add up. So we get this like very nice property, which is that the queries deteriorate additively, and the rate also deteriorates additively. So it's going to be well behaved when we iterate this operation to get bigger and bigger RLCCs. Great. Right, so nesting super well behaved. The queries go up by an additive amount, and the rate goes up by an additive amount. So now, like as promised, let's iterate on this operation. So if we have this like family of m LTCs, like LTC1 through LTCm, and if each of them has the same rate and the same distance and the same query complexity, and if each successive LTC's block length grows by this like fixed factor r, then the constant rate will add. So the loss in rate will be m epsilon, and the query complexity will also add. So we'll get like just by summing over the query complexity term over all of the m LTCs, plus the n1 term for like the trivial RLCC where you just read everything. So we get this very clean expression for both the rate and the query complexity. Right, and just to visualize what happens when you nest these like m LTCs together, you're going to start with like this largest LTC, and then you're going to like take the intersection with like these blocks of the next smallest LTC, and then you just keep going. And the depth of this sort of tree will be like log n, with the base being like the ratio of like the factor of how much the block length grows, which level. So then we have this like this is what our RLCC will look like. So what are the actual concrete parameters that we're going to plug into here? Right, so just copied from the previous slide, this is the rate and query complexity expressions. And we want C to be an asymptotically good RLCC, which means it has to have constant rate. So that means that because the rate is like 1 minus m epsilon, we'll have to choose epsilon to be like 1 over log n. And so by plugging this into the like Denner, Evra, Livne, Lubotsky, Moses C3 LTC paper, you notice that the query complexity, like Q, R, delta, kappa, all of these parameters of the LTC are like polynomially related to this epsilon. So when we set epsilon to be like 1 over log n, this query expression for the query complexity becomes polylog, which is what we wanted. So we're almost done. Just from this slide, like plugging in these LTCs with the appropriate epsilon. Now we have this RLCC, which has rate, which is actually like 1 minus little o of 1. Like if you notice here, sort of the ratio in how the block length grows with successive LTCs is going to be like a polylog. So the number, like m, the number of LTCs that we need is going to be like log n over log n, which is why it's actually like 1 minus 1 over log n, which is 1 over little o of 1. So the rate is actually really great. The query complexity, as I showed in the previous slide, is polylogarithmic, which is what we wanted. But the problem is that now the distance is like 1 over polylog n. Because when choosing epsilon to be 1 over log, it forces, like just like with singleton bound or any like classical bounds, if you have rate that close to 1, the distance has to be subconstant. So like just with this instantiation, right now the distance is like 1 over polylog n, which is not asymptotically good yet. But this turns out to be, you can just fix it in one step, which is that you can do nesting one more time with an LTC that actually has constant rate and constant distance. And your final RLCC will like basically inherit the rate and distance of this last LTC. So then that fixes everything. And so that gives you the RLCCs. If you like actually instantiate this, like if you actually look at the theorem and plug in like all the exponents from the polys, then this is the query complexity you get. Any questions?
69, where did that come?
So one of them comes from m, which is the number of levels, is like log, and then the other one comes from the r and the q and the kappa and the delta. I don't remember the exact numbers, but no. The first time we did this construction, we used the archive version of the LTC paper, and the exponent is actually like 1100 something. So it's not something like no one takes it seriously when I put the exponent on the board, but like it's not something that we were trying to go for.
15 plus 20 plus 30 plus 1.
The 69 looks very cool. We should maybe cancel the next talk.
Right. So this is what we wanted, and this is our main theorem. Some closing remarks. Right. As I mentioned, Gil Cohen and Tal Yankovitz were able to improve the exponent down to 2 plus a little o of 1, and just like basically you don't actually need as big a hammer as LTCs. You can use something weaker. It's basically the idea. Right. And so the obvious question, I guess, is like, can the query complexity go down to like log n or even like square root log n, or can the lower bound be improved? Another open question is like, can we get RLCCs with polylog queries, which is also simultaneously an LTC? So when we do this nesting, we lose the LTC property because we're taking like a subcode of an LTC, and it's not, you can't really test whether you're in the subcode. And this is actually something that people care about because, like I mentioned, sort of in the like PCP intuition, you want sort of local testability to eliminate the obvious garbage case and then this relaxed correctability to like try and extract information. So this is something that is in a lot of applications does matter that it's both simultaneously and ours is not. So this is like another direction, and that's all I have.
Some more time for questions. Okay. Thanks again.